The United States Navy entered World War II with the most expensive, most sophisticated torpedo ever built, and it failed 7 times out of 10. Before we go deeper into how this decision changed the Pacific War forever, make sure to subscribe for more history that actually happened. 20 feet of machined steel. 643 pounds of Torpex explosive. A wet heater combustion engine capable of pushing the weapon through saltwater at 46 knots. The Mark 14 torpedo represented 2 decades of engineering refinement, $10,000 per unit in Depression-era currency, and the classified hopes of the United States submarine force. It was designed to run silent beneath enemy hulls and detonate through magnetic influence, snapping the spine of a warship without ever touching it. In theory, it would render Japanese naval supremacy obsolete before the first shot of war. In practice, it became the most catastrophic weapons failure in American military history, not because it was poorly conceived, but because it was never properly tested. And the men who fired it into combat had no idea. December 1941. The Japanese strike on Pearl Harbor shattered the Pacific Fleet's battleship line, but left America's submarine force largely intact. 51 submarines, sleek, diesel-electric predators capable of diving to 300 feet and cruising 11,000 nautical miles without refueling, sat ready in ports from Hawaii to the Philippines. Each boat carried between 16 and 24 torpedoes in its forward and aft tubes. The Mark 14 was their primary weapon, the cutting edge of naval ordnance, designed specifically to prosecute a war the United States had been preparing for since 1922. The submarine doctrine was clear: choke Japan's supply lines, sink its merchant fleet, and strangle the island empire's ability to wage war. Within weeks, American submarines were prowling the sea lanes between Tokyo and the South Pacific, stalking oil tankers, troop transports, and cargo vessels. Commanders positioned their boats with textbook precision. They fired spreads of torpedoes at ranges under 2,000 yards. They heard the weapons strike the hulls with metallic clangs that echoed through the hydrophones. And then nothing. No detonation. No fireball. No sinking ship. Just the sound of a 3,000-pound torpedo bouncing off enemy steel like a hammer against an anvil. By March 1942, submarine skippers were filing furious after-action reports. Commander Tyrell Jacobs in USS Sargo fired 8 torpedoes at 2 separate merchantmen on Christmas Eve. 1941, 0 hits. He adjusted his approach, spent 57 minutes ensuring perfect firing solutions on 2 more targets, and launched for more torpedoes from 1,000 yards. All 4 failed to explode. Days later, he detected a slow tanker and fired 1 final shot at 1,200 yards with meticulous care. It missed entirely. Exasperated, Jacobs broke radio silence, a dangerous breach of protocol in enemy waters, to question whether the Mark 14 worked at all. His report joined dozens of others flooding back to Pearl Harbor and Fremantle. Torpedoes that ran in circles and nearly struck the firing submarine. Torpedoes that detonated prematurely 500 yards short of the target. Torpedoes that struck broadside and failed to explode. The submarine force was hemorrhaging opportunities, burning fuel and risking lives to achieve a hit rate that hovered near 30%. Japan's merchant marine, which should have been crippled within months, sailed on with impunity. The United States had spent the 1920s and 1930s engineering the Mark 14 under extraordinary secrecy. The Naval Torpedo Station at Newport, Rhode Island, the sole authority on torpedo design, testing, and production in the United States, developed the weapon in response to a specific problem: modern warships had grown too well armored. Torpedo belts, reinforced bulkheads, and anti-torpedo blisters rendered traditional contact explosions less effective. A direct hit against the side of a battleship might rupture outer compartments but leave the vessel operational. The solution lay not in a bigger warhead, but in a smarter one. If a torpedo could be made to explode beneath the keel of a ship, the blast would create an underwater gas bubble that would lift the hull, then collapse with catastrophic force, breaking the ship's back in 2. This required magnetic influence detonation, a sensor that could detect the change in Earth's magnetic field caused by a steel hull passing overhead, then trigger the warhead at the precise moment of maximum effect. The concept was elegant, theoretically sound, and borrowed from German magnetic mines used in World War I. The Mark VI exploder was the manifestation of that theory. Designated Project G53, it was developed behind what one historian called the tightest veil of secrecy the Navy had ever created. The device combined two detonation mechanisms, a magnetic influence sensor that would fire the torpedo beneath the keel, and a backup contact exploder that would trigger on direct impact. Development began in 1922. By 1931, when the Mark XIV torpedo entered production, the Mark VI exploder had been tested in a handful of controlled trials, none of which involved firing a live warhead at an actual target. Chief of Naval Operations William Pratt offered the hulk of the destroyer USS Erickson for destructive testing, but imposed two conditions: the Bureau of Ordnance could not use a live warhead, and if the test accidentally sank the ship, BU-Ord would pay to refloat it. Since Erickson was already scheduled for scrapping, the conditions were absurd. The Bureau declined. Instead, Newport conducted non-destructive trials using instrumented exercise heads fitted with cameras and small charges of gun cotton. The magnetic exploder would trigger the gun cotton, which would create a puff of smoke. Engineers presumed this meant the system worked. No one ever tested whether a full-scale Torpex warhead, traveling at 46 knots, would actually detonate as designed. Cost was the governing constraint. A single Mark XIV torpedo cost $10,000, the equivalent of more than $200,000 in modern currency. The Navy, operating under Depression-era budgets, refused to destroy expensive ordnance for the sake of testing. The philosophy was one of frugality masquerading as prudence. If the torpedo ran under the target net during trials, it was recorded as a successful hit because the magnetic exploder would have theoretically detonated. If the weapon failed to explode during a test, the torpedo could be recovered, refurbished, and reused. The entire development program for the Mark XIV cost $143,000, less than 15 torpedoes. Production ramped up slowly. By 1937, the Naval Torpedo Station at Newport, operating 3 shifts with 3,000 workers, produced exactly 1 torpedo per day. When war broke out in Europe in 1939, Newport had a backlog of unfilled orders worth $29 million. The Navy reopened the Alexandria Torpedo Station in Virginia and expanded the facility at Keyport, Washington, but production remained glacial. By December 1941, the submarine force had enough torpedoes to fight for perhaps 6 months at peacetime training rates. At wartime expenditure rates, the inventory would be gone in weeks. The Mark XIV itself was a marvel of mechanical engineering. 20 feet 6 inches long, 21 inches in diameter, it weighed just over 3,000 pounds with its Mod 3 warhead. The propulsion system used a wet heater design, high-proof alcohol fuel mixed with compressed air in a combustion chamber, the exhaust driving a steam turbine connected to contra-rotating propellers. The weapon could reach 46 knots for 4,500 yards, or throttle back to 31 knots for a range of 9,000 yards. A gyroscope-controlled steering, maintaining a preset course even if the torpedo was launched at an angle to the target's bearing. Depth control was managed by a hydrostatic valve linked to elevator fins at the tail. In theory, the Mark XIV could be set to run at any depth from 4 feet to 30 feet, holding that depth with precision while closing on its target. The magnetic exploder would sense the steel hull overhead, calculate the optimal firing point, and trigger 643 pounds of Torpex, a blend of RDX, TNT, and aluminum powder with 40% more explosive power than pure TNT. The detonation would occur directly beneath the keel, the blast lifting thousands of tons of warship upward, then letting it collapse into the void. Battleships would snap in half. Cruisers would sink in minutes. Carriers would vanish beneath the waves. That was the theory. Reality delivered something far different. The Mark XIV went to war carrying 3 catastrophic design flaws, each one invisible to peacetime testing, each one lethal to combat effectiveness. The first flaw was the simplest: the torpedo ran 10 to 11 feet deeper than its set depth. The second was more insidious: the magnetic exploder detonated prematurely or not at all, depending on latitude, target orientation, and pure chance. The third flaw would not be discovered until mid-1943, after nearly 2 years of combat, the contact exploder's firing pin would bend or shear off on direct impact, preventing detonation even when the torpedo struck the target perfectly. These defects did not exist in isolation, they masked one another, creating a fog of confusion that would take 21 months to penetrate. The depth problem had its roots in testing procedures. Newport ran trials using exercise heads, dummy warheads designed to be buoyant so the torpedo would float to the surface at the end of its run and could be recovered. The live Mod 3 warhead, loaded with 643 pounds of Torpex, was significantly heavier and denser. The additional mass changed the torpedo's trim, causing it to run deeper than the exercise head had run during testing. Newport's depth measurement system compounded the error. The depth and roll recorder, a device attached to the torpedo during trials to verify running depth, measured pressure through a port located on the tail cone, in exactly the same position as the torpedo's own depth sensor. When the torpedo moved through water, hydrodynamic flow over the tail cone created a pressure differential that made the sensor read shallower than the actual depth. Both the torpedo and the recorder suffered from the same error in the same direction, so tests showed the weapon running at the correct depth when it was actually 10 feet too deep. Static immersion tests, dunking a torpedo in a pool of still water, would have revealed the discrepancy, but those tests were never conducted with live warheads. Dynamic tests using exercise heads gave consistent results that were consistently wrong. The consequence was immediate and catastrophic. Submarine commanders set their torpedoes to run at 10 feet, expecting the magnetic exploder to trigger as the weapon passed beneath the target's keel. Instead, the torpedoes ran at 20 to 25 feet, passing harmlessly beneath shallow draft merchantmen and even cruisers. The magnetic exploder could not sense the target's hull at that depth. Skippers reported hearing their torpedoes strike the target. The hydrophone operator would detect a metallic clang as 3,000 pounds of steel collided with the enemy ship's hull, but no explosion followed. The submarines would be forced to crash dive as Japanese destroyers raced in with depth charges, the crews listening helplessly as their target steamed away unharmed. After-action reports filled with phrases like premature detonation, dud, broached, and ran erratic. The submarine force began to suspect something was fundamentally broken, but the Bureau of Ordnance in Washington insisted the weapon was sound. Captains were told their firing solutions were wrong, their approach angles poor, their depth settings miscalculated. The fault, BU Ord maintained, lay with the operators, not the weapon. Rear Admiral Charles Lockwood did not accept that explanation. In early 1942, Lockwood took command of the Southwest Pacific Submarine Force operating out of Fremantle, Australia. A career submariner and engineer, Lockwood had overseen torpedo development during the interwar years and understood the Mark 14's design philosophy. He also understood that 800 torpedoes had been fired in combat with appalling results. On June 20, 1942, Lockwood ordered the first real test of the Mark 14 since 1926. At Frenchman Bay near Albany, Australia, he had a fishing net suspended vertically in the water, marked at precise depth intervals. USS Skipjack, commanded by James Coe, fired a single torpedo with an exercise head set to run at 10 feet. The torpedo struck the net at 25 feet. The following day, James Fife, Lockwood's chief of staff, conducted 2 more test shots. Both ran 11 feet deeper than set. Lockwood sent the results to Washington. The Bureau of Ordnance was not amused. Neither was Chief of Naval Operations Ernest King, who reportedly lit a blowtorch under the Bureau of Ordnance. On August 1, 1942, 8 months into the war, BU Ord finally conceded that the Mark 14 ran deep. 6 weeks later, the Bureau admitted the depth control mechanism had been improperly designed and tested. The fix was straightforward: relocate the pressure sensor from the tail cone to the mid-body of the torpedo, where hydrodynamic effects were minimal. Submarine commanders, unwilling to wait for factory modifications, began setting their torpedoes to run at 0 depth, accepting the risk that the weapon might broach the surface and give away the submarine's position. Hits increased. Premature detonations also increased. With the torpedoes now running at the correct depth, the magnetic exploder began triggering, but not as intended. Torpedoes detonated 500 yards short of the target. They exploded directly beneath troopships without inflicting fatal damage. They fired while still turning onto their gyroscope course, wasting the shot entirely. The magnetic influence feature, designed to be the Mark 14 secret weapon, was behaving erratically. The problem was geomagnetic variation. The Mark 6 exploder had been calibrated for the Earth's magnetic field strength at Newport, Rhode Island, located at 41 degrees north latitude. Combat in the Pacific took place across a vast range of latitudes, from the Aleutians in the north to the Coral Sea in the south, each with different magnetic field characteristics. Near the equator, the field was weaker and oriented differently than at Newport. The exploder's sensitivity settings, locked in during development and considered too secret to adjust in the field, could not compensate. A ship traveling east-west would present a different magnetic signature than one traveling north-south. The exploder might trigger early, sensing the gradual change in the magnetic field as the torpedo closed on the target. Or it might not trigger at all, passing directly beneath the keel without detonating. Submarine skippers, desperate for solutions, began deactivating the magnetic feature and relying solely on the contact exploder. Some did this against direct orders, doctoring their patrol reports to hide the fact. Others, like Lieutenant Commander Dudley "Mush" Morton, the most celebrated submarine commander in the Pacific, openly refused to use the magnetic feature after returning from a patrol where his torpedoes had performed flawlessly in every respect except detonation. In May 1943, Lockwood, now Commander Submarine Force Pacific at Pearl Harbor, officially ordered the magnetic exploder deactivated. The decision came after Morton, whose aggressive tactics and confirmed kills had made him a legend, returned from patrol having failed to sink a single target despite perfect setups. If Morton could not make the Mark 14 work, no one could. Lockwood bypassed the Bureau of Ordnance and made the call himself. The magnetic influence feature, 2 decades in development, the Navy's classified secret weapon, was turned off. Submarine commanders would aim for contact hits. They would fire their torpedoes to strike the enemy hull directly, relying on the backup contact exploder to do what the magnetic sensor could not. Hit rates climbed immediately. Sinkings increased. The submarine force began to believe the crisis was over. It was not. The third flaw was about to reveal itself. July 24, 1943. USS Tinosa, under the command of Lieutenant Commander Lawrence Daspit, detected a lone tanker steaming without escort near the Caroline Islands. The target was Tonan Maru No. 3, the largest tanker in the Japanese fleet, 19,262 tons, fully loaded, dead in the water after suffering engine trouble. Daspit maneuvered into firing position. The setup was perfect, no destroyer screen, no evasive maneuvers, flat seas, clear visibility. He fired 4 torpedoes from the forward tubes. 2 struck the tanker amidships with audible clangs. Neither exploded. Daspit adjusted his angle and fired 2 more. Both hit. Neither detonated. He fired 2 more. Hits. No explosions. Daspit circled the crippled tanker for hours, methodically firing torpedo after torpedo, ensuring each shot was flawless. By nightfall, he had fired 15 torpedoes. 11 had struck the target. Only 2 had exploded, the first and the 11th. The tanker, damaged but afloat, was taken under tow by a Japanese destroyer and survived the war. Daspit returned to Pearl Harbor with 1 torpedo remaining. He refused to fire it, insisting it be sent to the laboratory for examination. He had just conducted the most expensive and frustrating live-fire test in torpedo history. Lockwood was apoplectic. His submarines were achieving perfect hits and the torpedoes still refused to explode. The magnetic exploder had been deactivated. The depth problem had been solved. There was no reason for the contact exploder to fail unless something was wrong with the contact exploder itself. Lockwood assigned Commander Charles Swede Mommsen, a submariner, an inventor of the Mommsen lung rescue device, to investigate. Mommsen and his team began drop testing Mark 14 torpedoes from a crane onto a steel plate, simulating direct impacts at various angles. What they discovered was both elegant and infuriating. The contact exploder used a mechanical firing pin inside the nose of the torpedo. When the torpedo struck a target, the pin was supposed to drive forward, strike a primer cap, and detonate the warhead. The system had worked reliably in the Mark 10 torpedo, which had a top speed of 30 knots. The Mark 14, however, traveled at 46 knots. At that speed, a head-on impact generated deceleration forces so extreme that the firing pin would bend or shear off before it could strike the primer. The pin guides, designed for lower speed impacts, could not handle the violent compression. The pin would jam, buckle, or break entirely. The torpedo would strike the target with enough force to dent the hull, but the warhead would not detonate. The problem only occurred with perpendicular hits, precisely the kind of shot submarine commanders were trained to make. A glancing blow at a shallow angle would allow the firing pin to function correctly, but a direct 90-degree impact would destroy the mechanism. The Bureau of Ordnance had never tested the exploder at full combat speed against a realistic target because doing so would destroy the torpedo. Mommsen's solution was simple: strengthen the firing pin and enlarge the guide channels to reduce binding. In September 1943, 21 months after the United States entered the war, the contact exploder was finally fixed. The first modified torpedoes reached the fleet in October. The transformation was immediate. Submarines that had struggled to sink even unescorted merchantmen suddenly became apex predators. USS Tang, commanded by Richard O'Kane, formerly Morton's executive officer aboard USS Wahoo, sank 33 ships in 5 patrols, a record that would stand for the remainder of the war. USS Flasher sank 100,000 tons of shipping. USS Barb, under Eugene Fluckey, conducted surface gun raids on Japanese coastal installations while continuing to sink transports and tankers. The submarine force, freed from the Mark 14's defects, began to throttle Japan's war effort. Merchant shipping losses climbed from modest totals in 1942 to staggering numbers in 1944. Oil tankers carrying fuel from the Dutch East Indies to Japan were sunk faster than they could be replaced. Troop transports carrying reinforcements to Guadalcanal, Saipan, and the Philippines vanished beneath the waves. Freighters loaded with rubber, tin, rice, and munitions settled to the seafloor. By 1945, Japan's merchant fleet had been reduced to a quarter of its December 1941 tonnage. The home islands faced starvation. Factories shut down for lack of raw materials. The Imperial Navy, unable to refuel its ships, kept its remaining carriers and battleships in port, conserving the dwindling oil reserves. The numbers tell the story. Between December 1941 and August 1945, United States submarines sank approximately 1,314 Japanese ships, totaling 5.3 million tons. That figure includes 201 warships, destroyers, cruisers, carriers, and submarines, and more than 1,100 merchant vessels. The submarine force represented less than 2% of the Navy's total personnel but accounted for 55% of Japan's maritime losses. No other weapons system in the Pacific War delivered such asymmetric lethality. The Mark 14 torpedo, once fixed, became the instrument of that destruction. A submarine could carry 24 torpedoes, reload tubes in minutes, and remain on patrol for 75 days. Japanese anti-submarine warfare was hampered by inadequate sonar, insufficient destroyer escorts, and a doctrine that prioritized offensive operations over convoy protection. American submarines exploited that weakness ruthlessly. They operated in wolf packs, coordinated attacks through radio intelligence, and intercepted convoy routes using decrypted Japanese communications. The Mark 14, firing at close range with a warhead that could crack a ship's keel, became the scalpel that severed Japan's logistical arteries. But the price of those victories had been paid in the first 2 years of the war, when the weapon did not work. Submarines had stalked targets for hours, maneuvered into perfect firing positions, expended irreplaceable torpedoes, and achieved nothing. Crews had listened to their weapons clang off enemy hulls, praying for an explosion that never came. Commanders had returned from patrols with empty tubes and empty tonnage reports, their credibility questioned, their judgment doubted. Some had been relieved of command, their careers ended, not because they failed but because their torpedoes failed. Tyrell Jacobs, the skipper who had broken radio silence to report the Mark 14's defects, was reassigned. Other commanders learned to keep silent, to work around the problems, to fire more torpedoes at shorter ranges in hopes that sheer volume would compensate for unreliability. The morale cost was incalculable. The strategic cost was measurable. Thousands of tons of Japanese shipping that should have been sunk in 1942 sailed unmolested, carrying fuel and supplies that prolonged the war. The bureaucratic cost was institutional rot. The Bureau of Ordnance had designed, tested, and certified the Mark 14 without ever conducting a live-fire trial under realistic combat conditions. When submarine commanders reported failures, BU dismissed the reports, blamed the operators, and insisted the weapon was sound. When Lockwood conducted his own tests and proved the depth mechanism was faulty, BU resisted the findings for weeks before conceding. When skippers deactivated the magnetic exploder against orders, BU accused them of cowardice and defeatism. The Bureau's arrogance was rooted in institutional isolation. Newport was the only facility authorized to design, test, and produce torpedoes, with no independent verification, no competing laboratory, no external oversight. The secrecy surrounding the Mark 6 exploder meant that even submarine force commanders did not fully understand how the weapon was supposed to function. Maintenance manuals were locked in safes. Sensitivity settings could not be adjusted in the field. When problems emerged, there was no mechanism for rapid iteration, no process for fielding emergency fixes. The torpedoes had to be sent back to Newport for modification, a process that could take months. The contrast with German and Japanese torpedo development is instructive. The German Navy encountered similar problems with its magnetic exploders early in World War II, during the invasion of Norway. Torpedoes detonated prematurely. Depth control was unreliable. Contact exploders failed. The Kriegsmarine immediately suspended the magnetic feature, investigated the failures, identified the design flaws, and implemented fixes within months. German submarines resumed operations with reliable weapons. The Imperial Japanese Navy's Type 93 long-lanced torpedo, meanwhile, had been tested extensively before the war, including live-fire trials against decommissioned warships. The weapon worked as designed from the first day of combat. Japanese destroyers used the long lance to devastating effect in night surface actions at Guadalcanal and the Java Sea, sinking cruisers and destroyers with single hits. The United States, despite its industrial capacity and technical expertise, had crippled its own submarine force through a combination of penny-pinching and hubris. The irony is that the Mark 14's theoretical design was sound. Magnetic influence detonation was a legitimate technological breakthrough. Running a torpedo beneath the keel to break a ship's spine was tactically brilliant. The wet heater propulsion system was efficient and powerful. The gyroscopic steering was precise. The contact exploder, when it worked, was lethal. Every individual component of the Mark 14 represented cutting-edge engineering. But the weapon had never been tested as a complete system under combat conditions, and the gaps between theory and reality had nearly cost the United States the Pacific War. If Japan had possessed a functional anti-submarine capability, if its destroyers had been equipped with effective sonar, if its doctrine had prioritized convoy escorts, if its depth charges had been used intelligently, the American submarine force might have been neutralized in 1942, before the Mark 14 was fixed. The United States won not because its weapons were superior, but because its enemies could not exploit the window of opportunity created by American incompetence. The lessons of the Mark 14 torpedo scandal extend far beyond World War II. Weapon systems are not abstractions. They are tools used by human beings under conditions of extreme stress, and they must be tested under those conditions before being fielded. Frugality in testing is false economy. The cost of a failed weapon in combat far exceeds the cost of destroying a dozen prototypes in realistic trials. Institutional arrogance is a strategic vulnerability. When the people firing the weapons report that the weapons do not work, the bureaucracy must listen, must investigate, must adapt. Secrecy, while necessary for protecting classified technology, cannot be allowed to prevent feedback from the field. The sailors aboard USS Tenosa, who watched 15 torpedoes strike a sitting target without sinking it, understood the Mark 14's failures better than any engineer at Newport. Their experience was data. Ignoring that data was criminal negligence. By the end of 1943, the Mark 14 had been transformed. The depth mechanism was fixed. The magnetic exploder was deactivated. The contact exploder was redesigned. Submarines began sinking Japanese ships at a rate that exceeded Japan's ability to replace them. The torpedo that had failed so catastrophically in 1942 became the weapon that strangled the Japanese Empire in 1944. Production ramped up. Newport, Alexandria, and Keyport combined to produce thousands of torpedoes, supplemented by the electric Mark 18, which used battery power instead of a combustion engine and left no visible wake. The Mark 14 remained in service with the United States Navy until the 1980s, upgraded with wire guidance and improved warheads, a testament to the underlying soundness of its design once the defects were corrected. But the weapon's legacy is not its longevity. Its legacy is the cautionary tale of what happens when theory is mistaken for proof, when testing is sacrificed for cost savings, when the men who use the weapons are ignored by the men who build them. The submarine force that emerged from the Mark 14 crisis was harder, more cynical, and more effective than the one that had entered the war. Skippers learned to trust their own judgment over the assurances of distant bureaucrats. They learned to improvise, to test their own weapons, to document failures with meticulous precision so that no one could dismiss their reports as operator error. They learned that the Navy's most expensive weapon could also be its most unreliable, and that survival depended on skepticism. The sailors who had fired dud torpedoes at enemy ships, who had watched their targets escape, who had risked their lives for nothing, they did not forget. When the Mark 14 finally worked, they used it without mercy. The Japanese merchant marine, which had numbered 6 million tons in December 1941, was a shattered remnant by August 1945. Tankers carrying oil from Borneo to Yokohama were sunk in the Luzon Strait. Freighters hauling iron ore from Manchuria vanished in the Yellow Sea. Troop transports reinforcing the Philippines were torpedoed before reaching port. The submarines operated with near impunity. Japanese convoy routes, decoded through signals intelligence, were ambushed with clinical precision. Escorts, spread thin across the Pacific, could not protect every ship. Depth charges, dropped hastily by destroyers that could not maintain contact with submerged targets, rarely found their mark. American submarines could crash dive to 300 feet and wait out the attack, then surface after nightfall and chase down the convoy. The Mark 14, firing in spreads of 4 or 6 torpedoes, would strike the largest ships first, tankers and transports that could not be replaced. The secondary targets, freighters and coastal vessels, would scatter, but there was nowhere to run. Another submarine would be waiting over the horizon. The psychological impact on Japanese crews was profound. Merchant sailors, already facing brutal conditions and inadequate pay, deserted in growing numbers. Captains refused to sail without destroyer escorts that did not exist. Ships sat idle in port, their cargoes rotting. Because no one would risk the voyage. The flow of oil from the Dutch East Indies, which had been the strategic justification for Japan's entire war, slowed to a trickle. Refineries in Japan shut down. The combined fleet's remaining battleships and carriers, designed to project power across the Pacific, were immobilized for lack of fuel. Pilots trained to fly Zeros and Judys could not train because there was no aviation gasoline. Factories producing tanks and artillery shells ran out of steel. The civilian population, already enduring strategic bombing, faced starvation as rice shipments from Indochina and Thailand failed to arrive. The submarine blockade, invisible to most Americans and almost entirely ignored in post-war popular memory, was as devastating as the firebombing of Tokyo or the atomic bombs dropped on Hiroshima and Nagasaki. The men who prosecuted that campaign did so with a weapon that had betrayed them for 2 years. They had fired torpedoes that ran deep, that exploded prematurely, that struck the target and failed to detonate. They had been told the weapon was perfect, that their aiming was flawed, that their complaints were unjustified. And then, in the summer and fall of 1943, the weapon was quietly fixed. No apologies were issued. No one at the Bureau of Ordnance was reprimanded. The institutional failures that had crippled the Mark 14 were buried beneath the flood of victory reports that followed. Submarines began sinking ships at rates that exceeded even the most optimistic pre-war projections. The Mark 14, once a punchline and a scandal, became a legend. But the sailors who had lived through the crisis knew the truth. They knew the weapon had been broken. They knew it had been fixed not by bureaucratic wisdom but by field commanders who had defied orders, conducted their own tests, and forced the Navy to confront reality. They knew that hundreds, perhaps thousands, of Japanese ships had escaped destruction because the torpedo had failed when it should have worked. History does not record the names of the merchant sailors aboard the ships that escaped. It does not tally the tons of fuel and ammunition that reached Japanese forces because a Mark 14 torpedo ran too deep or failed to explode. It does not measure the battles prolonged, the casualties inflicted, the months added to the war because the United States entered combat with a weapon that did not function. Those costs are diffuse, uncountable, woven into the fabric of a war that killed millions. But they were real. And they were preventable. A single live-fire test in 1935, using a decommissioned destroyer and a production model torpedo with a full warhead, would have revealed the depth problem, the magnetic exploder's unreliability, and the contact exploder's failure mode. The test would have cost $10,000 and the life of a ship already marked for scrap. The Navy refused to pay that price. It paid instead with 2 years of operational failure, with the lives of submariners sent into combat with defective weapons, and with the strategic opportunities lost in the opening phase of the Pacific War. By the time Japan surrendered in August 1945, the Mark 14 torpedo had become one of the most successful weapons in naval history. Submarines armed with the corrected version of the weapon had sunk more tonnage than all other American forces combined. The blockade of Japan was complete. The merchant marine was destroyed. The Imperial Navy, unable to fuel its ships or train its pilots, had been reduced to a coastal defense force. The Mark 14 had done precisely what it was designed to do once it was fixed. But the weapon's success cannot erase the scandal of its failure, nor the institutional pathologies that allowed the failure to persist. The Bureau of Ordnance, which had stonewalled submarine commanders for 21 months, never acknowledged its mistakes. The officers responsible for the inadequate testing program were never held accountable. The classification restrictions that had prevented field modifications were quietly lifted, but the culture of secrecy and arrogance that had created those restrictions remained intact. The United States learned from the Mark 14 scandal, but the lessons were learned slowly and incompletely. Future weapons programs would repeat the same mistakes: inadequate testing, overconfidence in theoretical models, resistance to feedback from operators. The difference is that the Mark 14's failures occurred during a war the United States was already winning. Through industrial and numerical superiority. The defects were catastrophic, but not fatal. In a closer contest, against a more capable enemy, the same failures might have led to defeat. That uncomfortable truth is the Mark 14's real legacy. It is a reminder that technology is not a substitute for rigorous validation, that bureaucracy is not a substitute for humility, and that the most expensive weapon is worthless if it does not work when the trigger is pulled. The men who fixed the Mark 14 did so through improvisation, insubordination, and relentless documentation of failure. Charles Lockwood conducted unauthorized tests and challenged the Bureau of Ordnance's authority. Swede Mommsen drop-tested torpedoes from a crane and identified the firing pin defect that Newport had missed for a decade. Dudley Morton deactivated the magnetic exploder and dared anyone to court-martial him. Lawrence Daspit fired 15 torpedoes at a stationary target and brought the last one home as evidence. These men were not rewarded for their initiative. They were ignored, resisted, and in some cases reassigned. But they persisted. And eventually, the weight of evidence became impossible to deny. The torpedoes were fixed. The submarines began to sink ships. The war, which might have ended sooner, ground toward its conclusion. The torpedo's journey from failure to triumph reflects a broader truth about technological warfare. Superiority is not determined by the sophistication of the design, but by the willingness to confront failure and adapt. The Mark 14 was conceived in an era when the United States believed it could engineer perfect weapons through pure intellect, when testing was seen as a wasteful formality, when the opinions of theorists outweighed the observations of practitioners. That mindset nearly lost the submarine war in the Pacific. What saved it was not better engineering. The fixes to the Mark 14 were mechanically simple, but institutional flexibility. The submarine force, operating thousands of miles from Washington, developed its own testing protocols, made its own tactical decisions, and forced the bureaucracy to accept reality. The transformation from a 50% failure rate to near total effectiveness took place not in a laboratory, but in the fleet, where commanders had the authority and the courage to challenge assumptions. The strategic consequences of the Mark 14's early failures extended beyond missed sinkings. In the crucial first year of the war, when Japan was consolidating its conquests across Southeast Asia and the Pacific, American submarines should have been interdicting supply lines, sinking troop transports, and creating logistical chaos. Instead, they were firing defective torpedoes at targets they could not kill. The Japanese military, expecting heavy submarine attrition based on pre-war assessments, was surprised by the relative ineffectiveness of American attacks in 1942. This allowed Japan to reinforce its island garrisons, build airfields, and establish defensive perimeters that would later cost thousands of American lives to overcome. Guadalcanal, where American forces struggled for 6 months to secure a single island, might have fallen more quickly if Japanese reinforcement convoys had been decimated by submarine attack. Rabaul, the fortified base in New Britain that became a major thorn in Allied operations, might never have been developed if the supply ships carrying construction equipment and materials had been sunk in transit. The Mark 14's failures allowed Japan to maximize its early strategic gains, turning what might have been a rapid American advance into a grinding war of attrition. Consider the calculus from Japan's perspective. In December 1941, Japanese war planners understood that their nation could not win a prolonged conflict against the United States. The American industrial base was too large, the resource disparity too great. Japan's strategy relied on seizing resource-rich territories in Southeast Asia, oil from the Dutch East Indies, rubber from Malaya, rice from Indochina, and creating a defensive perimeter that would be too costly for the United States to breach. The hope was that America, after suffering heavy casualties in attempts to retake fortified islands, would negotiate a settlement that left Japan in control of its new empire. This strategy depended entirely on Japan's ability to exploit captured resources and transport them back to the home islands. Tankers carrying oil from Borneo and Sumatra were the lifeblood of the Japanese war machine. Freighters hauling raw materials sustained Japanese industry. If those supply lines were severed, the entire strategic concept would collapse. The submarine force, even with defective torpedoes, posed an existential threat to Japan's war effort. If the Mark 14 had worked as designed from the beginning, Japan's merchant fleet would have been crippled by mid-1942, before the defensive perimeter could be consolidated. The war might have ended years earlier. The human cost of the torpedo failures is impossible to quantify precisely, but the outlines are clear. Every Japanese troop transport that escaped destruction delivered soldiers to islands where they would fight American Marines and Army infantrymen. Every tanker that reached Japan fueled aircraft that would strafe landing beaches and bomb fleet carriers. Every freighter that survived carried ammunition and supplies that extended the Japanese military's ability to resist. The Mark 14's defects, measured in terms of ships not sunk, translated directly into American casualties in battles that might have been avoided. The men who stormed the beaches at Tarawa, Peleliu, and Iwo Jima were fighting enemies who should have been starved of reinforcements and supplies. The sailors aboard carriers and destroyers in the Philippine Sea and Leyte Gulf were facing a fleet that should have been immobilized by lack of fuel. The bomber crews flying missions over Japan were striking factories that should have been shut down months earlier for lack of raw materials. The torpedoes' failures did not cause these battles, but they prolonged them, intensified them, and made them bloodier than they needed to be. The institutional resistance to acknowledging the Mark 14's defects also reveals a deeper problem within the Navy's culture. The Bureau of Ordnance was staffed by officers who had built their careers on the development of the Mark 14 and Mark 6 exploder. Admitting the weapon was flawed would have been an admission of professional failure. The classification system, which treated the magnetic exploder as the Navy's most closely guarded secret, made it impossible for submariners to understand why the weapon failed or how it was supposed to function. Maintenance personnel in the field did not have access to technical manuals. Commanders could not adjust sensitivity settings because the settings were classified. When torpedoes detonated prematurely or failed to explode, the skippers had no way to diagnose the problem because they did not know how the exploder worked. The secrecy that was supposed to protect American technological superiority became a prison that prevented American forces from adapting to combat realities. The German magnetic exploders, by contrast, were well documented in technical manuals available to U-boat commanders. When problems emerged, German submariners could adjust settings, disable features, and report detailed diagnostics. The German Navy's willingness to acknowledge and fix torpedo defects quickly gave it a functional weapon by mid-1940. The American Navy's obsession with secrecy and institutional prestige meant that the Mark 14 remained broken until mid-1943. The role of individual submarine commanders in exposing the Mark 14's flaws deserves recognition. These were men who had spent their careers being trained to trust their equipment, to follow doctrine, to respect the chain of command. When the torpedoes failed, they were told they were wrong, that their firing solutions were incorrect, their range estimations faulty, their observations unreliable. Lesser officers might have accepted that verdict and continued firing defective torpedoes in the hopes that the problem was with them, not the weapon. But men like Lockwood, Morton, and Daspit refused to doubt their own competence. They knew when a torpedo should have hit and did not. They knew when a setup was perfect and the result was failure. They documented these failures with obsessive precision, filling patrol reports with times, ranges, target speeds, gyroscope angles, and observed results. They demanded explanations. When the Bureau of Ordnance dismissed their concerns, they conducted their own tests, using their own torpedoes, their own submarines, their own initiative. Lockwood's net test at Frenchman Bay was not authorized by Washington. Daspit's decision to fire 15 torpedoes at Tonen Maru No. 3 and bring the last one home was a direct challenge to the Bureau's authority. These acts of insubordination were necessary because the bureaucracy had stopped listening. The fixes themselves, once implemented, were astonishingly simple. The depth problem required relocating a pressure sensor and recalibrating the hydrostatic valve. The magnetic exploder was simply deactivated. The contact exploder needed a stronger firing pin and redesigned guide channels. None of these modifications required advanced technology or sophisticated manufacturing. They could have been implemented in 1935, or 1938, or 1940 if anyone had bothered to test the weapon properly. The fact that they were not implemented until 1943 is a failure not of engineering, but of process. The Bureau of Ordnance operated without external oversight, without independent testing, without meaningful accountability. When the torpedo failed, there was no mechanism to force the Bureau to investigate. When submarine commanders reported problems, there was no requirement that the Bureau take those reports seriously. The Navy had created a closed loop where the people who designed the weapon were also the people who tested it, certified it, and defended it against criticism. That loop was only broken when Lockwood, operating from Pearl Harbor with the authority of ComSubPac, bypassed the chain of command and ordered the fixes himself. The aftermath of the scandal saw little in the way of consequences for those responsible. No senior officer at the Bureau of Ordnance was relieved. No one was court-martialed. No investigation was conducted into why the weapon had been certified for combat without adequate testing. The institutional memory of the Mark 14 failures faded quickly, buried beneath the flood of successes that followed the fixes. By 1945, the submarine force was sinking Japanese ships at a rate that exceeded the most optimistic pre-war projections, and the early failures were quietly forgotten. The official histories, written after the war, acknowledged the torpedo problems in passing but did not dwell on them. The focus shifted to the strategic achievements: the tonnage sunk, the convoys destroyed, the blockade completed. The Mark 14 became a symbol of American technological prowess, not a cautionary tale about bureaucratic failure. But the submariners who had lived through the crisis did not forget. They told stories, in wardrooms and reunion halls, about the torpedoes that did not explode, about the targets that got away, about the frustration of perfect setups wasted on defective weapons. They remembered the skippers who had been relieved of command, not because they failed, but because the torpedoes failed. They remembered the patrols where they had expended all their torpedoes without sinking a single ship, the long return voyages with empty tubes and empty tonnage tallies. They remembered the Bureau of Ordnance's arrogance, the dismissive responses to their reports, the insistence that the weapon was perfect and the operators were incompetent. And they remembered the moment when the torpedoes finally worked, when the warhead detonated as designed, when the target ship broke in half and slid beneath the waves. The satisfaction of that moment was tempered by the knowledge of how long it had taken, how many opportunities had been wasted, how much of the war had been fought with a weapon that should never have been fielded. The comparison with other navies is telling. The British Royal Navy, which had developed its own magnetic torpedo exploders before the war, encountered similar problems and solved them more quickly. British submarines in the Mediterranean reported premature detonations and duds in 1940. The Admiralty conducted tests, identified the problems, and issued fixes within months. By 1941, British torpedoes were functioning reliably. The German Kriegsmarine, as mentioned, fixed its torpedo problems after the Norway campaign and resumed effective operations by late 1940. The Soviet Navy, despite operating with older technology and less industrial capacity, fielded reliable torpedoes throughout the war. The United States, with its vast resources and technological expertise, was the only major naval power to enter combat with a fundamentally broken torpedo and keep it in service for nearly 2 years. The explanation lies not in technical capability, but in institutional culture. The Royal Navy and the Kriegsmarine had traditions of independent review and operational feedback. When weapons failed, there were mechanisms to investigate, adapt, and implement changes quickly. The United States Navy, at least within the Bureau of Ordnance, had developed a culture of insularity and defensiveness that resisted outside input and punished dissent. The legacy of the Mark 14 extends into the Cold War and beyond. The lessons about testing, feedback, and institutional humility were partially absorbed, but imperfectly applied. The Navy's next-generation torpedoes, the Mark 37, Mark 45, and eventually the Mark 48, underwent more rigorous testing before deployment, but problems still emerged. The Mark 48, which remains in service today, experienced guidance failures and warhead malfunctions in its early years. The difference was that the Navy, informed by the Mark 14 experience, responded more quickly to fix the problems. The culture of testing evolved to include live-fire trials, realistic target engagements, and operator feedback loops. The classification system was reformed to allow maintenance personnel access to technical data. The procurement process was restructured to include independent evaluation and competitive testing. These changes were direct responses to the failures of the Mark 14, though they were implemented slowly and unevenly across the Navy's weapons programs. The Mark 14 story also highlights the strategic importance of logistics and industrial capacity. Even with a 50% failure rate, the submarine force was able to continue operations because the United States could produce torpedoes in sufficient quantities to compensate for the defects. By 1944, American factories were producing hundreds of torpedoes per month, enough to sustain the submarine campaign even with wastage. Japan, by contrast, could not replace its lost merchant ships. Japanese shipyards, operating with limited steel and overstretched labor, could not match American sinking rates. Even when Japanese convoys were escorted by destroyers and patrol aircraft, even when American torpedoes occasionally failed, the attrition was unsustainable. Japan lost more ships each month than it could build. The submarine blockade succeeded not just because the Mark 14 eventually worked, but because the United States had the industrial base to keep firing torpedoes until the defects were fixed and the targets were destroyed. A smaller navy, or one fighting against an enemy with better anti-submarine capabilities, might not have had that luxury. The human dimension of the story is worth emphasizing. Submarine warfare in World War II was a brutal, claustrophobic endeavor. Submariners operated in steel tubes beneath the ocean, breathing recycled air, enduring depth charge attacks that could crush the hull, knowing that a single mistake could kill the entire crew. They went on patrols lasting 2 months, hunting enemy ships in hostile waters, far from support or rescue. When they fired a torpedo, they expected results. They had maneuvered into firing position, calculated the target speed and course, adjusted for wind and current, set the gyroscope angle and depth, and pulled the trigger. When the torpedo failed to explode, it was not just a tactical failure, it was a betrayal. The weapon they had been trained to trust, the weapon their lives depended on, did not work. And they were told it was their fault. The psychological toll of that experience cannot be measured in statistics or after-action reports. It eroded confidence, bred cynicism, and created a rift between the men in the fleet and the bureaucrats in Washington. When the torpedoes were finally fixed, the submariners did not celebrate the Navy's technical prowess. They grimly resumed their mission, determined to make up for lost time. The impact on Japanese civilian populations is another aspect of the story that deserves attention. The submarine blockade, once effective, did not distinguish between military and civilian targets. Tankers carrying fuel for battleships also carried fuel for factories and homes. Freighters transporting ammunition also carried food and medical supplies. The sinking of Japan's merchant fleet led directly to widespread starvation in the home islands by 1945. Rice rations were cut to subsistence levels. Cities faced fuel shortages during winter. Hospitals ran out of medicine. The civilian death toll from malnutrition and disease climbed into the hundreds of thousands. This was the strategic objective of the submarine campaign: to strangle Japan's economy and force surrender through deprivation. The Mark 14 torpedo, once it worked, became an instrument of that strategy. Every ship sunk was a step toward Japan's collapse, but it was also a step toward the suffering of millions of civilians who had no control over their government's decisions. The morality of unrestricted submarine warfare, which the United States had condemned when practiced by Germany in World War I, was not seriously debated during the Pacific War. The focus was on winning, on ending the war as quickly as possible, on bringing American servicemen home. The Mark 14 made that victory possible, but it did so at a cost that extended far beyond the battlefield. The technological evolution of the Mark 14 after the war is a footnote to the main story, but an interesting one. The torpedo remained in service with the United States Navy until the 1980s, upgraded with wire guidance systems, improved propulsion, and more powerful warheads. The basic design, a 21-inch diameter, steam-powered torpedo with gyroscopic control, proved adaptable to new technologies. Later versions could be guided from the launching submarine via a thin wire that unreeled as the torpedo traveled, allowing mid-course corrections and the ability to engage moving targets with greater precision. The Mark 14's longevity is a testament to the soundness of its core engineering. The problems that plagued it in World War II were not fundamental design flaws, but failures of testing and validation. Once those failures were corrected, the weapon performed as intended for 4 decades. The irony is that the torpedo could have worked from the beginning, if the Navy had been willing to spend the money and effort required to test it properly. The question remains, could the Pacific War have been shortened if the Mark 14 had worked from the beginning? The answer requires speculation, but the parameters are clear. In 1942, Japan's merchant fleet totaled approximately 6 million tons. The submarine force, operating with defective torpedoes, sank roughly 500,000 tons that year, less than 10% of the total. In 1943, with the torpedo problems gradually being solved, sinkings increased to over 1 million tons. In 1944, with fully functional Mark 14s and Mark 18s, submarines sank nearly 2.5 million tons. By 1945, there were barely enough Japanese ships left to target. If the 1944 sinking rate had been achieved in 1942 and 1943, Japan's merchant fleet would have been destroyed by mid-1944, a full year earlier than it actually was. That year represents tens of thousands of American casualties that might have been avoided, hundreds of ships and aircraft that might have been saved, and strategic operations that might have succeeded more quickly and at lower cost. The counterfactual extends to specific battles. The Japanese garrison on Guadalcanal, which fought American Marines from August 1942 to February 1943, depended on supply runs known as the Tokyo Express, fast destroyer convoys that raced down the slot to deliver reinforcements and supplies under cover of darkness. American submarines attempted to intercept these runs but achieved limited success due to torpedo failures. If the Mark 14 had been functional, more of these destroyer convoys would have been sunk or damaged, reducing the flow of Japanese reinforcements and possibly shortening the Guadalcanal campaign by months. Similarly, the Japanese defense of Rabaul, which required constant resupply by sea, might have collapsed earlier if the supply lines had been severed more effectively. The Philippines campaign in 1944, which saw fierce resistance from well-supplied Japanese forces, might have faced weaker opposition if the Mark 14 had been strangling supply convoys since 1942. These are not mere hypotheticals, they are logical extensions of the submarine force's actual performance once the torpedo worked correctly. The story of the Mark 14 is ultimately a story about the gap between theory and practice, between laboratory conditions and combat reality. Engineers at Newport designed a weapon based on sound principles of physics and hydrodynamics. They calculated the optimal warhead size, the ideal running depth, the correct magnetic field sensitivity. They ran simulations and conducted static tests. Everything worked on paper. But war is not a laboratory, and enemies do not cooperate with theoretical models. Ships travel at varying speeds and headings. The Earth's magnetic field changes with latitude and longitude. Ocean currents and wave action affect torpedo trajectory. Targets take evasive action when they detect a submarine. Depth charges create pressure waves that can knock a torpedo off course. These variables cannot be fully accounted for in peacetime testing, which is why realistic live-fire trials are essential. The Navy's refusal to conduct such trials, based on the cost of torpedoes and the reluctance to destroy test ships, was a decision that saved money in the short term and squandered lives in the long term. The lesson applies to all complex systems. Validation must occur under the conditions in which the system will actually be used, not under idealized conditions that make testing easier and cheaper. The broader implications for military procurement and weapons development extend well beyond the Navy and well beyond World War II. The Mark 14 scandal established principles that have been relearned, forgotten, and relearned again across generations of military technology. The first principle is that testing must replicate operational conditions as closely as possible. Laboratory tests, computer simulations, and controlled trials have value, but they cannot substitute for live-fire exercises against realistic targets in realistic environments. The second principle is that feedback from operators must be treated as authoritative data, not as complaints to be dismissed. The people using the weapon in combat understand its performance better than the people who designed it in peacetime. The third principle is that institutional pride must not override empirical evidence. When a weapon fails repeatedly in the field, the bureaucracy must investigate the weapon, not the operators. The fourth principle is that secrecy, while necessary for protecting classified technology, must not prevent the dissemination of information needed to maintain and employ the weapon effectively. These principles seem obvious in hindsight, but they were violated systematically during the Mark 14's development and deployment, and they have been violated in subsequent weapons programs despite the lessons of history. The echoes of the Mark 14 scandal can be seen in later controversies. The M16 rifle, introduced during the Vietnam War, suffered from jamming and reliability problems that were traced to inadequate testing with the ammunition and propellant actually used in combat. The Bradley fighting vehicle, developed in the 1970s and 1980s, faced criticism for being overdesigned and undertested against realistic threats. The littoral combat ship, introduced in the 2000s, has struggled with propulsion failures and cost overruns linked to insufficient validation before production. The F-35 fighter jet, still in development after decades and hundreds of billions of dollars, has faced repeated delays due to software problems and performance shortfalls that might have been identified earlier with more rigorous testing. Each of these programs repeated elements of the Mark 14 story: ambitious design goals, insufficient realistic testing, resistance to operator feedback, and bureaucratic defensiveness when problems emerged. The fact that these patterns recur suggests that institutional memory is fragile, that the lessons of the Mark 14 are known but not internalized, and that the incentives within military procurement favor optimism and secrecy over skepticism and transparency. The human legacy of the Mark 14 is carried forward by the submariners who survived the war and the families of those who did not. 52 American submarines were lost during World War II, taking more than 3,500 men to the bottom. Some of those losses were due to depth charges, mines, and aircraft attacks that no weapon could have prevented. But others might have been avoided if the submarines had been able to sink their targets more quickly and escape before counterattack. A submarine that fires 8 torpedoes and achieves 2 hits must remain in the area longer, exposing itself to greater risk, than a submarine that fires 4 torpedoes and achieves 4 hits. The Mark 14's failures force submarines to linger in dangerous waters, to make multiple attack runs, to expend their entire torpedo loadout on targets that should have been sunk with half as many weapons. That prolonged exposure increased the likelihood of detection and counterattack. Some of the submarines that were lost might have survived if their torpedoes had worked correctly the first time. The names are inscribed on memorials: USS Wahoo, lost with all hands in October 1943. USS Tang, sunk by one of its own circular-running torpedoes in October 1944. USS Grunion, USS Amberjack, USS Scorpion, USS Grenadier, 52 boats, 3,500 men, some lost to enemy action that might have been avoided if the Mark 14 had functioned as designed from the beginning. The final irony of the Mark 14 story is that the torpedo's ultimate success obscured the magnitude of its early failure. By the end of the war, the Mark 14 had become a symbol of American technological superiority, proof that American submarines had dominated the Pacific. The official narratives, written in the flush of victory, emphasized the tonnage sunk and the strategic impact, not the 2 years of dysfunction that preceded the success. The submarine force's achievements were real and extraordinary, but they were achieved despite the Mark 14, not because of it. The weapon worked in 1944 and 1945 because field commanders had forced the bureaucracy to fix it, because submariners had risked their careers to challenge authority, because engineers like Swede Mommsen had conducted the tests that Newport should have conducted a decade earlier. The credit for the submarine campaign success belongs to those men, not to the Bureau of Ordnance that had certified a broken weapon for combat. The Mark 14 torpedo entered service as the most advanced undersea weapon in the world and became operational as the most unreliable. It was fixed not through institutional wisdom, but through institutional defiance. It sank over 1,000 Japanese ships and helped win the Pacific War, but it did so only after squandering 2 years of opportunities and costing lives that should never have been lost. The weapon's legacy is not its technical sophistication or its eventual effectiveness, but the enduring lesson that even the most expensive, most carefully designed system is worthless if it has not been tested under the conditions in which it will actually be used. The gap between what the Mark 14 was supposed to do and what it actually did in the first years of the war represents one of the most consequential failures in the history of military technology. The fact that the failure was eventually corrected does not erase the cost of the delay, nor does it excuse the arrogance and incompetence that created the problem in the first place. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world.